Hello everyone, my name is Tiago. Welcome again to my channel, Code Tab. And today we're solving problem number 14 from projecteuler.net in this series of videos that we're solving Project Euler's problem. Let's read the description of this problem. It says like this, the longest Collatz sequence, that's the name of the problem. The following iterative sequence is defined for the set of positive integers. N implies that the next element of the sequence is n over 2 if n is even. Otherwise, the next element of this sequence will be 3 times n plus 1 if n is odd. Therefore, using the rule above and starting with 13, we generate the following sequence. So the sequence is like 13. 13 is an odd number, so 3 times plus 1, we get 40. 40 is even, so we divide by 2, we get 20. 20 is also even, we divide by 2, we get 10, which is also even, we divide by 2, we get 5. 5 is again odd, which 3 times 5 plus 1, we get 16, which is even, divide by 2, 8, divide by 2, 4, divide by 2, 2, and divide by 2, 1, right? So it says here that it can be seen that this sequence is starting at 13 and finishing at 1 contains 10 terms. Although it has not been proved yet, the Collatz problem, it is thought that all starting numbers eventually finish at 1. This is true. This problem is still unsolved problems in mathematics. There is no mathematical proof that states that any starting number will eventually finish at 1, although conjecture states that this could be the case, but it's not proven. It's one open problem in mathematics if you want to give it a try. Right, so it says here which starting number under 1 million produces the longest chain. So this is the problem that you're trying to solve, right? It just states here one special note that once the chain starts, the terms are allowed to go above 1 million, right? So how can we solve this problem? This problem requires us to explore this sequence. Starting from a number, we should try to get the next number until we end until we meet the end of this sequence. We can do this in a simple way. We can just start with a number and make a condition. If this number is even, we divide it by 2. If this number is odd, we make this multiplication plus sum. And once we reach the end, we just get our result and calculate how many terms we passed through. In this sense, there are 2 ways to solve it. There is the recursive way and there is the iterative way. Let's just explore first the iteration way, and then we can also try the recursive way. Let's just create our problem 14 here. Add package, problem 14. Let's add, and we also shall create our problem 14, right? Okay, so let's start then the implementation. I wish to create a function called Collatz, right, that receiving a number, like an initial n, which is the type integer, it should give us the number of terms that the Collatz sequence have for this number. So the return should also be an integer. So this function should then count the number of the terms of the Collatz sequence starting at a given n. So this should be the starting number. And this should be the result, should be the number of terms of the Collatz sequence. Right, so how should we implement this function then? My idea then is to start from a counter. We're going to have to define a variable that would be the count, right? It always starts at 1 because 1 will always be in this sequence. So I will start with that, right? And I'm going to start with some sort of iteration here. And let's call it n. So while n is bigger than 1, this is our stopping part, right? So what I'm going to check here is if n mod 2 equal to 0, then my n will become n divided by 2, right? That's the case of the even numbers. Otherwise, if it's odd, it's going to become 3 times n plus 1, right? In both cases, I'm just going to count plus equal 1, right? Because in both cases will be a term of this sequence. And in the end, we return the count. We can give it a try with this count Collatz function for our starting example here, which is 13. Let's see if we get the same result, right? So let's just run this problem 14.py. Oh, I forgot to put the print. So print this. And we get 10 terms, which is exactly the number of results that we have here, the number of terms of this sequence. So we need to check then which starting number that is smaller than 1 million that produces this longest chain, right? So let's just store here longest chain. We can start it at 0. And the longest number, right? Which is also, we can start it at 0. So we can start with numbers in the range until 1 million, right? This is a million. Yes, it is. And then we can just count the Collatz, right? Count Collatz number. Sorry, n, right? So if the count is bigger than the longest sequence that we have, the longest chain, then our longest chain receives the count, and our longest number receives n. And in the end, we just print the longest number. This should do the trick. The only question is whether this function is fast enough to deal with all of the numbers below 1 million, right? Because there's still a lot of computation there. Let's see. 3, 2, 1, go. And as you can see, it is taking a while to go through all of the numbers there, right? I'm not sure if we're going to be able to go under a minute. Yes, we have a result here. The result is this number, but you notice it took a few seconds to go through all of that. Let's give it a try to see if this is the right number of our problem. Check. And it's right. It says that the answer is correct. Right, but we noticed that it took a few seconds to go through that. Let's just explore here how long it took. But I think it took a few seconds. So I'm going to go here to put a simple profiling. And here I print datetime, the datetime.now minus start time. Opa, datetime. Let's try again. Yeah, it took 12 seconds to run. It's still under the constraints of Project Euler. I saw in one of the forums that Project Euler's problems are designed to be solved under 1 minute of a computation in a normal computer. Yeah, but I believe we can do better than this. As we can see here from this sequence, in many cases, we're gonna end, the only case that we reach 1 is through 2, and 2 is through 4, 4 is through 8, 8 is through 16, right? So there are several situations in which we're going to have to pass and compute repeated numbers of this sequence. It would be lovely if we can just store some of these numbers somewhere in a sort of dictionary, in a sort of vector, so that if we find that that sequence, it's just easy to just pick from where they stopped and that's it, right? So this is quite simple. We can just make a global variable here, which would be our memory. That would be our dictionary here. And and then we can just build this memory as we compute these numbers. So in this case here, once we get to this point and we get the Collatz of one initial number, we can just store it in our memory. That this would be our count, right? But if we are in the middle of the sequence and we reach one number that is already in our memory, we can just get it from there and break in that point. So for example, if n is in memory, all we can do here is just to update our count, right? Our count would become the memory in the position n minus 1 because we're starting from 1, right? So we have to remove that. And we can just break from that point onwards. This should significantly improve our computation because once we find a number that we already computed before, we just get that number. We don't have to continue computing and wasting time. So let's try to see if this solves our problem. Okay, so restarting. And now it took 1 second approximately to solve. So that's a great improvement in our code, right? Yes, and the answer is still correct. It's the same answer. Just before we finish, I would like to say that we can also solve this in a different way, which is a recursive solution. Implementation for a recursive solution would be def count Collatz recursive, right? It's the same header. We receive the number, and the output is also a number, right? An integer. In this case here, this is like count the numbers in the Collatz sequence through a recursive approach, right? And the number here is just going to be like the given integer, and it will return, in this case, just the number of terms of the Collatz sequence for the given number, right? So let's just put one space here, and that's it. So we need to think first, since this is a recursive function and it will call itself multiple times, we need to think on the conditions in which this function will stop and start returning. The first condition is if we find the number 1, which is the end of our sequence. So if the number is equal to 1, then we return 1, right? This is the first stage. The second condition is if we find the number already in memory. In this case, since we're keeping a global variable as memory, so we can just check if the number is present in the memory. So if number in memory, then we just return memory for the number, right? If that's not the case, then we check the conditions of the Collatz sequence, right? So that's the same thing. If number mod 2 equals 0, then our count function, right? We can establish it here. Count is equal to 0. We can initiate it like this, and then we can just receive it by calling the same function. In this case, we call it, since it's even case, we just divide it by 2, right? So number divided by 2 plus 1, right? Plus 1, because we're calculating the number of terms. The other exception is in case if it's an odd number, so we do the same thing, right? So we count the recursive, but in this case 3 times the number plus 1, and then we also sum another one here. Once we have this number, we can just call the memory, right? Just store this number in memory. So we store here the number, and then we just return the count, right? So that's the condition here that we have. In this case here, since the division might not be an integer, so it's giving me an error, so we'd better make an integer division, which is in each case it's going to be, because we assured ourselves that this number is divisible by 2, right? We don't need to initiate this. That should be okay. Yes, this should solve the problem. Let's give it a try just to make sure, right? In this case, we want to do the same thing, but we're going to call the recursive n. It should be as fast as the previous function. Let's find out. Yes, it is pretty much similar speed, right? So yeah, so these are the two solutions to this problem: the iterative solution to the Collatz sequence and the recursive solution, right? We are leveraging the memory use, so we have to store previous computations to make use of, instead of wasting computations, right? In order to make the problem 10 times fast. Thank you so much for watching. If you like the video, please like, share, subscribe, and I see you in the next video.